Let's... This is our infant universe. Everything that will ever exist, everything that will ever happen, all begins here, within this tiny bundle of energy, smaller than an atom. And right now, history as we know it is about to mysteriously begin. For reasons we may never know, our universe suddenly erupts.
In a millionth of 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 a second, it went from a size smaller than an atom to bigger than a galaxy. Whoosh!
What you're seeing is energy, and it's one key to understanding everything that will unfold in... Within a fraction of a second, the Big Bang creates all the energy that will ever exist. All the energy that will power the stars, that will fuel anything that ever lives. All the energy that you will ever consume dates back to the beginning of time.
When you put gas into your car, you're tapping energy that was created during the Big Bang. You're tapping the energy of the universe itself.
We're only a few minutes into our 2-hour journey, but already 380,000 years have passed. You are about to witness the birth of your original ancestors, the first atoms. This is hydrogen. The universe will use it to make everything in the world around us.
Hydrogen is like a baseball team. You say, what player do I want to start my team with? Well, if I want to start a universe, I want to start it with hydrogen. Because from that, with a lot of heat and a lot of pressure, you can build more kinds of atoms.
The first atoms blast through the early universe. And luckily for us, they don't spread out evenly. Because in those tiny pockets with more atoms, gravity, the great sculptor of the early universe, begins to work its magic. The first galaxies are beginning to form, revealing a timeless secret of the universe.
Insignificant though this bottle of compressed hydrogen gas looks, it marks the beginning of the world's largest and most powerful particle accelerator chain, culminating in CERN's spectacular Large Hadron Collider. Hydrogen atoms from this gas cylinder are fed at a precisely controlled rate into the source chamber of a linear accelerator, CERN's LINAC-2, where their electrons are stripped off to leave hydrogen nuclei. These are protons and have a positive charge, enabling them to be accelerated by an electric field. Their journey to eventually take part in ultra-high energy collisions similar to those following the Big Bang can now begin. This initial acceleration has caused LINAC-2 to be likened to the lumbering first stage of a huge rocket. By the time this packet of protons leaves LINAC-2, it'll be travelling at 1/3 the speed of light. It's about to enter the booster, stage 2 of the rocket if you will. In order to maximise the intensity of the beam, the packet is divided up into 4, one for each of the booster's rings. Straight acceleration is now impractical, and the booster is circular, 157 metres in circumference. In order to accelerate the packets, they are repeatedly circulated, and the electric field is now pulsed, in the same way that you push a child on a swing each time they reach a certain point. Magnets exert a force on the passing protons at right angles to their direction of motion, and so powerful electromagnets are used to bend the beam of protons round the circle. The booster accelerates the protons up to 91.6% of the speed of light and squeezes them closer together. Recombining the packet from the 4 rings, it's then flung on into the proton synchrotron, by analogy stage 3 of our rocket. Let's just follow 2 such proton packets. The proton synchrotron is 628 meters in circumference, and they circulate for 1.2 seconds, reaching over 99.9% of the velocity of light. It's here that the point of transition is reached, a point where the energy added to the protons by the pulsating electric field cannot translate into increased velocity, as they're already approaching the limiting speed of light. Instead, the added energy manifests itself as increasing mass of the protons. In short, the protons can't go faster, so they get heavier. The microscopic kinetic energy of each proton is measured in units called electron volts, and now the energy of each proton has risen to 25 giga-electron volts, or GeV. The protons are now 25 times heavier than they are at rest. The packets of protons are now channeled into stage 4, the superproton synchrotron, a huge ring 7 kilometers in circumference, designed specifically to accept protons at this energy and increase it to 450 GeV. Soon, the packets of protons will be energized sufficiently to be launched into the orbit of the gigantic Large Hadron Collider, or LHC, which lies between the Jura Mountains and the Alps, and straddles both France and Switzerland. Lying deep underground, it has a circumference of 27 kilometers. There are 2 vacuum pipes within the LHC containing proton beams travelling in opposite directions. Using ultra-sophisticated kickers to synchronize incoming packets with those already circulating, one vacuum pipe has injected into it protons which will circulate clockwise, and the other protons which will circulate anti-clockwise. The counter-rotating beams cross over in the 4 detector caverns, where they can be made to collide. The energy of the collision is double that of the individual opposing protons, and it's the debris from these collisions that is tracked in the detectors. For half an hour, the SPS injects protons. Finally, there are 2,808 packets. During this time, the LHC adds extra energy to each proton, whose velocity is now so near the speed of light that it goes round the 27-kilometer ring over 11,000 times each second, getting a boost of energy at each revolution from the pulsed electric field. Finally, each proton has an energy of 7 tera-electron volts, and they're 7,000 times heavier than at rest. The magnetic force needed to keep the beams bending to the ring is so enormous that nearly 12,000 amps must flow through its electromagnets. This is achieved by making the LHC colder than outer space, so that its magnets become superconducting. Now the protons are ready to collide in the detectors. A steering magnet finally brings them onto a collision course. The total energy of 2 protons colliding in the LHC is 14 tera-electron volts and reproduces similar states to moments after the Big Bang. Particle tracks from these collisions will be analysed by computers connected to the detectors, and it's hoped these tracks will give a new insight into the very birth of our universe, how our universe has evolved, what governs its behaviour today, and where it's going in the future.
A force must act. For anything at all to happen in the universe, a force must act.
Scientists have built the biggest particle accelerator ever. I'm standing 100 meters below the ground at CERN in Geneva, and this is the CMS detector, part of the largest and most complicated scientific experiment ever attempted. Here, we'll recreate the conditions that were present in the universe less than a billionth of a second after the Big Bang. How do we recreate those extreme conditions here on Earth? Well, you need one of these, the Large Hadron Collider. 27 kilometers in circumference and filled with over 2,000 superconducting magnets, each at 1.9 Kelvin. That means that they're colder than the space between the stars. Inside here, we accelerate protons to 99.999999% the speed of light before bringing them into collision inside 4 giant detectors. Why would we build all this to understand the universe? The universe today seems almost impossibly complex, full of planets, stars, and even life itself. But over centuries of experimentation, we found that the complexity is really a property of an old, cold universe. When the universe was much younger and much hotter, it appeared to be much simpler. And so it's here that we're going to recreate the conditions that were present in the very earliest times to hopefully reveal that underlying simplicity. I wouldn't like to predict what will happen at the LHC. It's like guessing what we'll find on our first journey to the stars. But the giants of history would have loved access to this machine because science is about exploring, and the only way to uncover the secrets of the universe is to go and look.